Hello and welcome back. So let's continue looking at this question where we have a rational function, but if we plug -5, if we're trying to find the limit as x approaches -5, we normally want to plug -5 into our function, but we don't get a number. We get 0 divided by 0, which is not a number, so it's hard to tell what this limit is. But we were able to take this rational function and show that, we actually can cancel x plus 5 off the top and bottom, which means that our rational function is equal to x minus 3 as long as x is not -5. So if I were to actually graph this, we would have x minus 3, so 1, 2, 3, and our function is going to look something like something like this. And then out here at -5, instead of actually going through this, we have an empty circle. So we essentially skip -5 and just blow right by it. Our function has a hole there. This function is exactly equal to x minus 3 everywhere, except for except when x is equal to -5, in which case our function doesn't exist. But if we're talking about a limit, we're talking about what happens as we get closer and closer to -5. The limit doesn't care what happens at -5. At -5, our function value could jump up there. At -5, our function value could exist right there, or maybe just doesn't exist at all. A limit doesn't care about what happens right at that point. It only cares about what happens really close to that point. So when I'm taking a limit as x approaches -5 of this guy, and we see that, close to -5, we are just equal to x is equal to -3, and we're never concerned about what happens at -5. I can just take that limit. So the limit as x approaches -5 of our function is going to be equal to that same limit. Is going to be equal to our reduced fraction, because this limit doesn't care about what happens at -5. It only cares about what happens close to it. And this is a rational function. This is something that I can just plug -5 into. Oops. So this is just going to be equal to -5 minus 3, which is -8. So we can reduce rational fractions, and then plug it in, provided that, again, we're not dividing by 0. Here, when we reduce the fraction, we just get a nice polynomial. So again, just to sort of reiterate, the limit of a function as x approaches a, this doesn't care about what f of a is. F of a might not exist. F of a we might jump to another value before continuing on. It doesn't matter what happens at a exactly. The limit only cares about what f of x looks like as it gets close to a. So that's enough about these sorts of limits. I want to do another couple of limits where we look at another phenomenon. So here, I have the limit as x approaches infinity of x plus 1 over 2x plus 3. And right away, I go, this is a rational function, right? Let me just plug in my limit. So I'll take infinity plus 1 over 2 times infinity plus 3. This doesn't make any sense. Don't do this, because infinity is not a number. You can't plug it in. I can't take 2 times infinity. You can't take 2 times apple. You can't take 2 times, the word the. Infinity is not a number. You can only multiply and add numbers. So this doesn't work. So we need to find a new way. And the trick that I'll show you relies on one other fact. So if you recall from last time meaning maybe 2 lectures ago, the limit as x approaches infinity of 1 over x, so this is something that we've done before, is equal to 0. And again, to draw a little graph, 1 over x looks like this. As x gets really, really big, and I'm dividing by a really big number, this is getting closer and closer to 0. 1 divided by 10, 1 divided by a million, 1 divided by a trillion. These are really, really small numbers in the sense that they're close to 0. So this limit is close to 0. So I'm going to abuse that inside of my function here. So let's take the limit as x approaches infinity of x plus 1 over 2x plus 3. And I want to use this fact by dividing the top and bottom by x. What happens if I divide the top of this fraction by x? Well, I'm going to, so let's just write this down exactly what I'm doing. I'll show all my steps here. So I'm going to divide the top by x, and I'll divide the bottom by x. As in, I'm going to multiply by 1 over x and multiply by 1 over x. So far, I haven't changed the function much, have I? I can now no longer plug 0 into my function because I can't divide by 0. But who cares about 0? I'm going off to infinity. And 0 is nowhere close to infinity. So again, the function doesn't care about like what happens directly at the limit or what happens away from the limit, only what happens close to it. And 0 is far enough away from infinity, I don't care. So let's take this limit, and I will distribute. So x times 1 over x is 1. 1 times 1 over x is 1 over x. And then as I multiply the bottom, I'll get 2x times 1 over x, which is 2, plus 3 times 1 over x. Let me write that a little bit nicer. And then here, I can use all the properties of limits that we used before. And I will, I'm running out of space here. I'm going to do something I shouldn't and continue above. So I apologize for the mess here. I haven't given myself enough space. I'm going to use all the properties of limits that I talked about before, where I can take the limit of the top of the fraction and the limit of the bottom of the fraction. When I'm adding things, I can take the limit of each one individually. And I'm going to do this all in one big step. So first of all, if I take the limit of the top of the fraction, I can take the limit as x approaches infinity of 1, plus the limit as x approaches infinity of 1 over x, divided by, and then the bottom of the fraction, I can then split that into the limit as x approaches infinity of 2, plus the limit as x approaches infinity of 3 over x. And again, I'm going to, this will be fine. So I have the limit as x approaches infinity of 1. Well, 1 is a constant function. It never changes height. So even as x gets really big, the limit is still 1. As x approaches infinity of 1 over x, we just said that this is 0. The limit as x approaches infinity of 2, again, 2 is a constant function. It never changes. And the limit as x approaches infinity of 3 over x, again, I can think of this as the limit as x approaches infinity of 3 times the limit as x approaches infinity of 1 over x, and the limit, and that limit is 0. So 3 times 0 is 0. And simplifying this, we get that this is just 1/2. So this trick here is just divide everything, divide the top and bottom of the fraction by x. And we canceled out everything, and the only things that we were left with were constants, like the 1 and the 2, or some 1 over x's, like these guys. And this is our trick. We want to divide the top and the bottom by x to the n. Maybe we have higher powers of x in there, and we want x to the n just to be the highest power of x that we see, and this will take care of things going off to infinity. So let's go through one more of these, just so that we know exactly what we're doing. So I've got the limit as x approaches infinity of 3x squared plus 2x plus 1 over 4x cubed plus 3x squared plus 2x plus 1. So again, I've got a rational function, polynomial divided by polynomial, except I'm going off to infinity. And it's hard to take x to infinity because we will get infinity. So what I'll do is I'll divide everything by the highest power of x that I see, which is x cubed. So let's write this down. 3x squared divided by x cubed is going to be 3 over x. 2x divided by x cubed is going to be 2 over x squared. 1 divided by x cubed is going to be 1 over x cubed. 4x cubed divided by x cubed is 4. 3x squared divided by x cubed is going to be 3 over x. 2x divided by x cubed is 2 over x squared. And 1 divided by x cubed is going to be 1 over x cubed. And then let's write down this gigantic limit here. So again, I can take the limit of the top and the bottom. So the limit of the top, I can split apart. Divided by the limit of the bottom, the limit as x approaches infinity of 4, plus the limit as x approaches infinity of 3 over x, plus the limit as x approaches infinity. You can begin to see why I'm doing a lot of extra steps that maybe I don't need to here, but I just want to do this for completeness sake. And here, I'm going to do a couple of things. I'm just going to pick one of these, and I'll show you what happens to it. So I'm going to pick this one here, and let's simplify this. So just as an aside, I have the limit of 2 over x squared. So this is going to be the limit of the limit as x approaches infinity of 2 times the limit as x approaches infinity of 1 over x squared. Again, I can pull apart a fraction into 2 times 1 over x squared, and 1 over x squared is the same thing as 1 over x quantity squared. This is 2, so this is 2, this is 0, so this whole thing is 0. And what you'll notice is that this is 0, 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 and this is 0. As x gets really big, if I'm taking 1 and dividing by x cubed, I'm dividing by a huge number, so that's going to be close to 0. The same sort of logic applies to each one of these except this guy, which is a constant function, so that's really easy to write down the limit of. So this is equal to 0 plus 0 plus 0 over 4 plus 0 plus 0 plus 0, so we get a limit of 0. So rational functions are nice. When we look at things algebraically and we use our algebraic properties, things will cancel quite often as long as we have a couple of tricks. For instance, for taking limits as x approaches infinity.